Welcome, that's Daniel Schleifer from Racy Applications, and I'm going to show you how to process high-specs Mjolnir data for single-band raw imagery. So this is, it's in multi-band hyperspectral ones. First, what data do we have? We have some data which is from VNIR spectrometer. We have two data sets in one directory and combine it with a part status file. The data itself is raw data, so that's not rectified, but still you need the GCS file from parts for the processing because it contains all the necessary parameters. If you look at the spectra, it's the VNIR only with all these absorptions which should be removed later. Now the first step for the DROACOR processing is to import the Mjolnir data. So I'm gonna import Neo Mjolnir, and I got to change, first I select a directory with just one band, and I got to change the filter. So it needs image.bsq in this case. Often it will be float32.bsq or something similar for standard naming in high-specs Mjolnir. So I take image, I just enter image.bsq, and push return, and then I get the found file. So these two files will be imported later. The calibration file is not required, so default is fine because it's calibrated data. You don't need external calibration file. For the reference image, you just take one of them. Maybe I take the second one this time. This one is used for the spectral calibration and should be the most stable ones if you got a few of them. And for the ground elevation, this is taken from the GCS file, so you can take it from the metadata. I'm going to write this to a different output directory. Here it's already some data there, but you can also create it. It would be created dynamically if it's not there yet, this output directory. So now we are ready to import. So we import the data. It will go for it, and it will also calibrate the VNIR detector. Of course, obviously there is no sphere data, so it can't correct that one. And it imported to both files with the new spectral positions, and it also created a lookup table file to the output directory. So the import went well. If you look at the data here, the height above ground is 220 meters. The ground altitude is 1600 meters. So this is a Cuprite Nevada scene, and the solar zenith angle is reasonable at 46 degrees. That's fine. Let's proceed to the processing. So we select DROACOR processor. We take the same directory again, same input directory. So I got to change the filter to image.bsq. Now I got these same two files, while the parameter files had been written to the output. Parameter files are JSON files, .json files. Maybe we have a look at one of them. They will be in the output directory, and it will be something like that. So it contains all the metadata required for the processing. You even could change this JSON files if you want to change some parameters manually for the processing, but usually they just are kept as is. The output should be again the same output directory with a reflectance extension. This is standard extension for DROACOR processing outputs. We do a polishing, medium polishing. We do interpolation in 1400 volt. It's not applicable for the VNIR, but I don't want to interpolate, so I could also choose no interpolation, and I don't need to remove any bands for this case. I keep the unpolished data for comparison purposes, but and then I could run the DROACOR. I overwrite existing outputs there, and it will take a while for the processing because there are 200 bands to process, and it's a full scene. As you see, it doesn't take too long in this case, so it's done in a few approximately 1 or 2 minutes. So processing has finished now, and we're gonna proceed and have a look at the outputs. So the processing took about 1 minute per scene. Here you see the 61 seconds of the second scene which has been processed. Let's have a look at the product. So we got this reflectance output. The polished, unpolished is that one. And if you look at the spectra, they may look like that. And if you want to look at the polished output, you can have a look at pH data. And we also show the spectrum of this one. This is the polished and the unpolished spectrum. And have a look at the same. Let's try to link them, the two of them. So I push position here and get position there. So that's how you can compare the two spectra against each other. So this is what the polishing does. It really removes these very small remaining variations in the spectrum. No interpolation has been applied in the 940 absorption band, so it's all optimized for what we have in the data. This is the output of the polished one. Now this is a mineral area with a lot of materials. So if you look down here, it's a standard Cuprite Nevada scene. We could also go to a product generation like for minerals. So I do a mineral detection based on this data. Well, it's VNIR only, but we can still try if you can see some differences. We have this reflectance output. Maybe I only take one of the scenes. I maybe take the 2D. So it is the first one. And I select a few, maybe just 3 of them. And maybe some, where is the kaolinite? That's the ones I wanted to look at. And this will create now a mapping of these minerals. We can have a look at the 3 spectra in the VNIR. They show some differences, so it should be feasible to use them for spectral angle mapping. So if you do the calculation, it will take a few minutes, a few seconds to do the spectral angle mapping. It's inverse spectral angle mapping. This means it's 1 over the spectral angle. So the larger the values, the closer the spectra are to the target spectra. Now you can have a look at the output. This is this material output, matte BSQ, that one. It has 3 bands for the goethite, hematite and kaolinite. And we can check these out and see how they are distributed. So there seem to be some spot. So RGB, so the red one is goethite, the green one is hematite, and the blue one is kaolinite. And we see that it's really feasible to discriminate these materials in this Cuprite Nevada scene. Okay, so much about this processing and what we can do after DROACOR processing with our data. Thanks a lot for the attention, and